Welcome viewers to the fourth and last segment of the first lecture for the online series of lectures for the course of Algebraic Topology 2. In the previous segment, we computed the simplicial homology groups of Klein bottle. We'll begin this segment with the statement of a theorem concerning the homology groups of the compact surface real projective plane. Let me state the theorem first and then I'll prove it. Theorem 3. Let P2 be the complex obtained from the labeled rectangle pictured below. So let me label the top edge of this rectangle by A, B, C, D, and the bottom edge by the reverse direction D, C, B, A, and the left edge by A, F, E, D, and the right edge by D, E, F, A. Okay, and from this label rectangle we see that the diametrically opposite points are identified in this rectangle, which is exactly the same as the two discs with opposite points or antipodal points being identified. In this way, this point is identified with this point, and this point is going to be identified with this point. This point is going to be identified with the diametrically opposite point located here, and so on. Okay, this is the two disc, right, with the boundary of this two disc being antipodally identified. We call this D modded out by an equivalence relation, and the equivalence relation is the relation that identifies antipodal points on the boundary. Okay, so this is the figure corresponding to real projective plane P2. Now we need to first see how we can get the real projective plane out of this two disc with the boundary as pictured in the figure on the right. Okay, but before that, let me state the remaining part of the theorem, the underlying space. So once the gluing is done here, what we get is the complex P2. Okay, and the underlying space of this complex P2 space mod P2 of the complex P2 after identifications are made along the edges, obeying the labels is called the projective plane or the real projective plane. Projective plane. We then have, once we have this topological space, the homology, this first homology group of the complex P2 is isomorphic to the finite group, the two-element group Z over 2, and the second homology group of this complex P2 is trivial. Okay, all right. So now it's time to prove this theorem. So let me erase what we have here. Okay, and then prove it. DCBA. Okay. All right. So as before, the boundary A is G of mod of BDL. Okay. So there is the boundary of this labeled rectangle, as we can see here. This is the boundary of the labeled rectangle, and under the gluing map, this boundary, the topological space corresponding to this boundary is going to be mapped to a subspace here, okay, and that is homeomorphic to a unit circle that we are going to see first. Okay, so it's immediate here that this is equal to this, because it's a diametrically opposite points being identified, right? Something like this. Each of the diametrically opposite points are being identified. All right. Now what we are going to see is that the complex P2 can be obtained from here by cutting out a small 2-disk here, and whatever we are left with is homeomorphic to a Mobius band, and that Mobius band has a boundary which is homeomorphic to a circle, and we have to attach that Mobius band along its boundary, that is a circle, to the boundary of the cutout unit disk, cutout small disk. Okay, so let's see this first, how we get it. And this surgical argument is bought from the Oxford lecture notes by Jutu and Lackenby. So I'm gonna use their surgical argument to see how we obtain real projective plane from this base. Okay. All right. So let me erase everything at this point. Um, so we have already drawn it. So this is the boundary of a two disk that is going to be identified this way, and what we have inside is the interior of the two disk. Okay, and we are going to call it D, modded out by the equivalence relation of identification of diametrically opposite points along the boundary of this two disk. Okay, D modded out by this equivalence relation is the two disk with antipodal points identified on the boundary okay, which we already mentioned is nothing but homeomorphic to the label complex L, okay, which we drew earlier on the left. Right, I'm not going to draw it again. Okay, on the boundary, which, as we already mentioned, is homeomorphic to the labeled rectangle or labeled complex whose underlying space is, of course, the rectangle labeled complex L. Now, first, I want you to decompose the two disk D into an annulus M, and whatever we are left with is a two disk, is a smaller two disk, and the smaller two disk, so that attaching the inner circle of the annulus along the boundary of the smaller disk gives the full two disk D. Okay, all right, so let me draw the fact here. So just think about this two disk without this equivalence relation. It's a two disk, plain two disk. Okay, we can cut out a smaller disk here from this two disk and get an annulus here, right? So this is the annulus M, all right, and when we attach the inner circle of this annulus to the boundary of this smaller 2 disk, we get the full 2 disk here. Okay. All right. So we therefore can say that attaching a 2 disk. So now we form this guy. Okay. This guy. This is M, modded out by the equivalence relation of antipodal points being identified along the outer circle of the annulus. Okay. So this is the quotient space, and this quotient space is precisely this space. Okay. So once we have this quotient space, which is annulus modded out by the equivalence relation, and when we attach this guy to the boundary of this smaller 2 disk, okay, what we get is precisely this. The 2 disk modded out by the equivalence relation of the antipodal points being identified along the boundary of the 2 disk. Okay. All right. Good. So let me erase everything. Now what we are going to do is to show that this annulus modded out by the equivalence relation is homeomorphic to a Mobius band. Okay. This is what we are going to show now with a surgical argument that we borrowed from that Oxford lecture note that we already acknowledged, and so we are going to show that. So what we have at the end is this Mobius band, and we are going to glue this Mobius band. We are going to glue this Mobius band along its boundary to the boundary of a 2 disk. Okay. Because the Mobius band has a boundary which is homeomorphic to a circle, and the unit disk has its boundary as a circle, so they can be glued together to form a space, and that space is nothing but our projective space or projective plane. Okay, real projective plane. So let's see that this indeed gives us the Mobius band. Okay. All right, so let me draw that annulus, this guy first. This is the annulus, right? This is just plain annulus. Now, once we have this plain annulus, we apply the orientation to have this quotient space. This point needs to be identified with that point, diametrically opposite point, and this needs to be identified with this piece. Okay, this is this guy is the annulus modded out by the equivalence relation of the identification of the diametrically opposite points along the outer circle of the annulus, and this can be shown to be this can be identified with the figure that I'm drawing here. So I keep the upper part to be the same, the orientation along the outer circle of the annulus, and then I prescribed an orientation along this boundary. Okay, so this side, this edge is going to be identified with this edge, and this edge with 3 arrows is going to be identified with this edge with 3 arrows. Okay, so we get exactly the same figure on the left after the identifications are made. Okay, it's clear. Then this figure, so let me put this shading in the interior of the annulus. Okay, now this is the same as this. So what I'm doing is stretching this edge downwards and stretching this edge upward, so that I have a rectangular shape on top. Okay, with the top edge of the rectangle directed to the right, and the left edge of the top rectangle directed downwards, right, and the right edge of the rectangle being directed upwards. And this is, nothing is happening along the bottom edge. Similarly, we have a lower rectangle whose bottom edge is directed to the left. Okay, and the left edge is directed upward, and the right edge is directed downward. Okay, and the top edge of the lower rectangle does not have any orientation given. Okay, so at this point these two rectangles are dissociated from each other. Okay, and now, okay, so I have to put the shading. Both the rectangles are shaded. Okay, now what I do is the swapping, right? Swapping the top rectangle with the bottom rectangle, so that the bottom rectangle now becomes the top rectangle. Okay, this is the top rectangle now. This is the top rectangle, and the top rectangle here becomes the bottom rectangle. Becomes the bottom rectangle. So the bottom rectangle is oriented this way. Okay, so let me write it here. Swapping the top rectangle with the bottom rectangle. Okay, now this is going to be the same as, now I am going to, since these two rectangles are dissociated from each other, I can always reflect the top rectangle about this vertical line, and that gives me the following top rectangle. So the left edge now becomes the right edge, and the right edge now becomes the left edge of the top rectangle, right? And the orientation is also reversed. So this is the top rectangle, and the bottom rectangle stays the same. The bottom rectangle stays the same. So this can be obtained from this by reflecting the top rectangle about a vertical line. Okay, and this is homeomorphic to a Mobius band. Okay, it can be identified. Okay, and this edge is going to be identified with this edge, and this edge is going to be identified. This edge is going to be identified with this edge, and this edge is going to be identified with that edge, so that I just have, you know, this left edge is going to be identified with the right edge. Okay, and this is the whole Mobius band. Okay, so what we have found is that this guy, the annulus, modded out by the equivalence relation of identification of the antipodal points along its boundary, is nothing but the Mobius band, right? And what it means is that if we take this Mobius band, whose boundary is homeomorphic to a circle, right? We know that the boundary of a Mobius band is homeomorphic to a circle, and we have this smaller 2 disk that we cut out of the annulus. Okay, its boundary is also a circle, and we can join these 2 circles to get the real projective plane. Okay, all right, good. Now let G from mod L is the underlying space of the label rectangle that we drew earlier, and mod P2 is the underlying space of the complex P2 that we obtain from the gluing procedure that we just described. Okay, and this is the underlying gluing map. Let G be the respective gluing map. Okay, so we just saw that that A, which is G of BD of L, in this case is homeomorphic to a circle, is homeomorphic to a circle. This circle is precisely the circle along which the Mobius band is attached to the unit disk. So let me reiterate. This circle is precisely the circle along which the Mobius band is attached to the 2 disk. So remember that we cut out a smaller 2 disk to form an annulus, okay, and the annulus with the prescribed identification along its boundary becomes the Mobius band, right? And the boundary of the Mobius band can be attached to the cutout smaller disk, to the boundary of the cutout smaller disk to give the real projective plane. And hence, the boundary of the Mobius band, which is glued to the boundary of the 2 disk, is precisely this guy. Okay, which we denoted by A. Okay, now we denote by Z1 this one chain AB plus BC plus CD plus DE plus EF plus FA. So let me draw this guy here once again, because we need this rectangle, label rectangle now. This is A, B, C, D, E, F, A. This is E, F, D, okay? And now this is D, C, B, A. We are going to call this sigma 1, this sigma 5, this by sigma 2. You remember that all the 2 simplices here in the label rectangle L are oriented counterclockwise. This is again, this is sigma 3, and this is sigma 4, and this is sigma 6. Okay, good. And we call this vertex H and this vertex J. So Z1 is the linear combination of all these elementary 1 chains given by this equation. Condition 1 and 2 of theorem 1 hold as before. Why? Because under the identification, the orientations of the 2 simplices that we have here in the label rectangle L are not disrupted. They stay intact under the identification. So the proofs of 1 and 2 go as before and they hold. So there are two additional results. So let me write those results. Every one cycle carried by A is this guy which is homeomorphic to a circle, carried by A is a multiple of Z1, this guy. Okay, so how does it happen? Let us quickly have a look at it. So you see that it can be seen as the boundary of a complex, right? It's a one-dimensional complex. A, B, C, D, E, F. Right? So so look at this vertices A, B, C, D, E, F, and then A. So back to A here. All right. So let C be one cycle carried by A, right? Which is homeomorphic to a circle, and this guy is homeomorphic to a circle, what we have here. Then C is equal to N1 AB, A comma B plus N2 B comma C plus N3 C comma D plus N4 D comma E plus N5 E comma F plus N6 F comma A, which means that the value of this one cycle C on the oriented one simplex A comma B is N1. The value of this one cycle on the oriented one simplex F comma A is N6, and so on, where N1, N2, N3, N4, N5, and N6 are certain integers. So what is this one chain? Sorry, this is not a one chain. C is a one cycle. So del 1 C is supposed to be 0, right? This should be a zero chain, right? And this zero chain is supposed to be 0, identically 0, since C is a one cycle. So let us compute C del 1 C here, which is N1 B minus A plus N2 C minus B plus N3 D minus C plus N4 E minus D plus N5 F minus E plus N6 A minus F, which is equal to N6 minus N1 times A plus N1 minus N2 times B plus N2 minus N3 times C plus N3 minus N4 times D plus n4 minus n5 times E plus n5 minus n6 times F is equal to 0. And since this is equal to 0, we must have n1 equal to n6, n1 equal to n2. We also have n2 is equal to n3. We have n3 is equal to n4. We have n4 is equal to n5. And we also have n5 is equal to n6, leading to the following equation. Leading to n1 is equal to n2 is equal to n3 is equal to n4 is equal to n5 is equal to n6. Therefore, if C is a one cycle carried by A, which is homeomorphic to a circle, then C is equal to nz1, where n is just an integer. Okay, right? Now we have to prove that del 2 gamma is minus 2 times z1. I just erased that rectangle. I gotta draw it again. A, B, C, D, E, F, A, B, C, D, E, F, A. This is H and this is J. Okay, I'm going to keep this for the rest of the proof. All the two simplices here, sigma i's, are oriented counterclockwise. Okay, counterclockwise as before. So one computes this one chains del 2 sigma 1 is equal to B comma A plus A comma H plus H comma B, while del 2 sigma 4 is going to be equal to B comma A del 2 sigma 4 is going to be B comma A plus A comma J plus J comma B. Okay, one can immediately see that the value of del 2 sigma 1 plus del 2 sigma 4 on the oriented one simplex a comma b is minus 2, right? Because this can be written down as minus a comma b, and so is this one minus a comma b, and when you add them up you have a coefficient minus 2 coming in front, right? Thus the value of the one chain del 2 gamma, which incorporates this sum on the oriented one simplex a comma b is minus 2, right? One can similarly go on to verify that del 2 sigma 5 here, delta sigma 5 is a comma f, right? A comma f, which we can write as minus f comma a plus f comma h plus h comma a, right? And one can also write del 2 sigma 6 as here. Here again one starts with a comma f, which one can write as minus f comma a plus f comma j plus j comma a. Okay, so that one verifies immediately that the value of delta 2 sigma 5 plus delta 2 sigma 6 on f comma a is again minus 2. That is, the value of this one chain del 2 gamma on f comma a is minus 2. Right? Okay, so let me erase this part. I need some room. Now one can verify that the value of del 2 gamma, the one chain del 2 gamma, vanishes on each of the oriented one simplices which don't belong to this boundary. Okay, something like this. Okay, so one can pick up the appropriate two simplices to show that their contribution cancel out or drop out from the expression of del 2 gamma, right? And the value of the one chain del 2 gamma on each of the other one simplices, oriented one simplices along the boundary L, like B comma C, C comma D, D comma E, and E comma F is minus 2. The value of del 2 gamma on each of these simplices is minus 2. We just have shown that del 2 gamma on A comma B is minus 2, we similarly have shown that the value of del 2 gamma on A comma or on F comma A, right? We have shown that its value on F comma A is minus 2 as well, right? One can similarly show that the value of del 2 gamma on each of these 4 oriented one simplices is also minus 2. That way, one evaluates del 2 gamma to be equal to minus 2 times A comma B, minus 2 times B comma C, minus 2 times C comma D, minus 2 times D comma E, minus 2 times E comma F, minus 2 times F comma A, to be equal to minus 2 times Z1. This is our equation number 17. Okay. Good. So we have now 4 facts, and we can gather these facts and compute the homology groups of the real projective plane. Let us see how we do that. Let C be one cycle on P2, on the complex P2. Okay. Then we know that we know from the third fact that we have proved a while ago that C is equal to n times Z1 with n belonging to the set of integers, right? While if C is a one cycle on P2 it's worth noting that by 1 it is carried by A, which is homeomorphic to a circle, right? And if it satisfies C equal to del 2D for some 2 chain D on P2, for some 2 chain D on P2, so that since C is carried by A, del 2D is also carried by A. Carried by A, then by 2, D is a multiple of gamma. D is equal to P times gamma for some integer value of P, right? So that one obtains del 2D is equal to P times del 2 gamma, right? And we have seen that del 2 gamma is, a while ago we have seen that del 2 gamma is minus 2 Z1, right? Minus 2 Z1, so that we have minus 2P Z1. This is del 2D by 4. Okay. Hence an element of B1 P2, hence an element of B1 of P2 one boundary on the complex P2 is an even multiple of Z1. Okay. Now we set two one cycles C and C prime on P2 to be equivalent if C minus C prime is equal to 2p times Z1 for some p in the set of integers. Okay. All right. So we have the space of one cycles, right? Which can be written down as this. And we claim that, so we put an equivalence relation on this space of one cycles. What is that equivalence relation? Two one cycles C and C prime are going to be declared to be the same, or they will be equivalent if they differ by an integer multiple of Z1, right? Okay, so in other words, all the integral multiples of Z1 are divided into two classes. So these are the integral multiples of Z1, all right, which are called one cycles on the complex P2. And these all integral multiples of Z1 are divided into two classes. Okay. Even integral multiple and odd integral multiple of Z1. All the even integral multiples of Z1 is set equal to the zero element of the quotient group. What is that quotient group? It's Z1 P2 quotient out by B1 P2, which is nothing but the first homology group of the complex P2. All right, so what is the zero element? The zero element is all the even integral multiples of Z1. They are set to the zero element of this set of equivalence classes, okay? And right. And the non-zero element of H1 of P2 represents the equivalence class of odd multiples of Z1. One therefore has this guy to be isomorphic to Z over 2, two element group, right? 0 and 1. Okay, now it's time to compute H2 of P2, the second homology group of the complex P2. Let D be a two cycle. Then from the definition of a two cycle, we know that, in fact, from the definition of cycle, it follows that del 2D is equal to 0. So that the value of del 2D is 0 on every one simplex not belonging to boundary of L. It means that its value is 0 on every one simplex not belonging to the boundary of L. In other words, del 2D is carried by boundary of L trivially. Del 2 of D is carried by BDL trivially. And once del 2 of D is carried by BD of L, 2 applies. So it means that the two cycle that we started with is a multiple of gamma for some p in the set of integers. Okay, it means that del 2d is equal to p del 2 gamma, and we have found earlier that del 2 gamma is minus 2z1 from equation number 17. So it follows that this is equal to minus 2pz1 from 17. Okay, but since d is a 2 cycle, we must have del 2d to be equal to 0, which means that minus 2pz1 is equal to 0. Therefore, p is equal to 0. Right? Which means that since d is equal to p gamma, d is equal to 0. What does that mean? It means that the 2 cycle that we started with is trivial. Okay. In other words, the group of 2 cycles on the complex P2 is trivial. It means that the second homology group of the complex P2 is also trivial. Since this is Z2 of P2 modded out by the 2 boundaries on P2. Okay. Alright, so let me summarize what we have gotten for the real projective plane. We have gotten that the first homology group for the complex associated with the real projective plane is a finite group, which means that there is no free part here, only the torsion part is available. And for the second homology group of the real projective plane is trivial QED. This is what we wanted to prove. Thank you for attending the first lecture for the course of Algebraic Topology 2.